In this video, I want to introduce two methods of constructing correlation networks. Okay, let's see the first method, the plot network functions under FWF525 and the ggplot2 package. Okay, let's load the libraries that will be used, including ggplot2, Bagan, Plur, Scales, Grade, Reshape2, FWF525. Okay, and then set the directory to the folder where our files locate. Okay, for this webinar, I will use microbial sequence data analyzed by mother software. From mother analysis, I got two files, shared and taxonomy. So I then combine the two files into mother data that includes abundance and taxonomy information. In the meantime, I prepared CSV file with detailed information such as sample ID, sampling sites, virus abundance, bacteria abundance, virus to bacteria ratio actually. So this is metadata, includes all this information of the sequences. I impart this information to mother meta. Using read CSV function. So then I use merge FWF525 function to combine all this information to mother FWF525. Now we can see the rank of classification names of bacteria. So in my study, I have 3 replicates. So I try to merge 3 replicates per sample into one for further comparison across samples. Okay, here we got merged mother FWF525. Now let us see the functions of make network and plot network. Okay, for network, we need a FWF525 file, which we generated from above. Type is samples, and the distance we can set as G-code. Max distance as 0.4. So for plot network, we need G, which is an iGraph class object created either by the convenience wrapper make network or directly by the tools in the iGraph package. We can also set types and samples, but here we are plotting a network of bacterial taxa association network, so we set our type as taxa. We can also choose color and shape. In this example, I use shape to represent phylum and color to represent the class. I choose to use line weight as 0.4 and have no labels. Okay, let's see how it goes. Okay, Here it is. From this network, we can tell different classes of bacteria were closely correlated. Acetobacteria, Planctomycetes, Proteobacteria played very important roles in shaping the microbial community. And this is cool. It tells us information. However, there's another way to show the microbial community correlation network, which I am going to show next. It is more powerful and can show much more details. This is called SparCC. So it can produce very similar correlation networks, but we can learn a lot of more information from the networks. For SparCC, we still need to use R to process data first and prepare the dataset as input for SparCC. So let us load the library first. The same process to formalize the sequence data from mother, and the same mother file sec was generated by this codes. Okay, the same mother file sec was generated. So for preparation of the dataset and the input for SparCC, we generate the mother file sec on class level, which is the third level on taxonomy. Using length function, we can see we have 78 classes identified, and we generate these data classes with 1 to 78. And a CSV file was generated to show the labels of these bacterial classes. Yeah, it is fast. Then we use filter taxa function to select all classes that have more than 50 sequences and exclude the taxa with less than 50 sequences. Write out the CSV file, including the data we need, and then transfer the CSV file to ACF through terminal. So this is a file we generated. Let's see. Here it is one. So we need to transfer this file to ACF and analyze the data on ACF using SparCC. So this is the code we use to transfer our mother class SparCC CSV. It is located on in the folder on desktop. This is destination on acf.cedu. This is the SparCC folder, and until FWF525. Okay, I have transferred this file onto ACF. So let's see if it is there. Yes, the file is here. So the file has been uploaded to ACF. So on ACF, I have downloaded and installed the sparcc to my directory. And I have prepared all the codes I need for the sparcc analysis in the Word file. So I can copy the codes and perform the analysis one step by one step. First, we need to transform CSV file to TXT file using this code. Because the sparcc can only read TXT file. Inside the working directory FWF525, we need to make the directory of basic CORR and PVOS. So the directory has been created. And go back to sparcc bitbucket directory, including the sparcc source command here. And run sparcc Python command. Copy the code, paste here, run. Okay, it's done. Here is code. We can see there's an I here. The I means the number of the number of inference interactions to average over. -A means the algorithm for calculating correlation, which includes sparcc, Pearson, Spearson, and Kendall. To make shuffle datasets for calculating p-value using make bootstrap function. Here's a command. Let's copy it. Run. Yeah, here it comes. Okay, next. We then calculate sparcc using shuffled datasets with exactly the same parameter setup. Then calculate the former dataset. Name all the output files consistently, numbered sequentially, and with a TXT extension. As I have 200 bootstrap permutations, I will write a for loop to do this work. This is the for loop code. I'll copy this code, paste. So you can see the code began running. So it will take a while to finish sparcc calculation using 200 simulated datasets, two-sided p-value calculation. So let's wait here. Okay, down. The for loop code has been finished. So we have calculated the correlation matrix and two-sided p-value for each correlation. And now we are ready to go back to R for further analysis and visualization of the networks. Before we go back to R, we need to transform the files we need to CSV file, which is easily accessed by R. So transform both sparse correlation matrix and two-sided p-value from TXT to CSV format and transfer to local computer and upload to R to start network realization using iGraph package. Let's do that. This is the code. So we have transformed the CSV file, TXT file to CSV file. So now we need to secure copy the files onto computer. So now we have downloaded the correlation sparse file and the p-value file to the local computer. So back to R, use read CSV function to transfer the sparse correlation to mother sparse correlation. And make it as matrix. We can see the first 4 lines of the sparse correlation. Use read as CSV to transfer two-sided p-value to sparse p-value and turn it to matrix. And we can also see the first 4 lines of p-values. And then we can read sparse correlation matrix and the p-value matrix to iGraph. And edge information p-value to the network. Here it is. And then add edge weights to the network. We can see the information of the edges. Generate vertices data frame from whole network. Remove edges that from and to the same nodes. We don't need these edges. Then create a new network using the above vertices and edge data frame. We have mothernet 1 and mothernet 2. So for mother net 2, we have 46 nodes and 2070 edges. Then convert directed network to undirected network using the as undirected function. So the final step is to simplify the network from mothernet 3. We need to remove non-significant edges. So let's summary. The p-value smaller than 0.01. So we can see we have 185 edges with p-value smaller than 0.1. And we have 342 edges with p-value smaller than 342, smaller than 0.05. So since we have enough edges with p-value smaller than 0.01, which is very significant, now we delete all edges that have p-value larger than 0.01. And also we delete the edges that have no edges. Deleted the nodes that have no edges. And further simplify the network based on degree. So let's see. Delete the vertices which have smaller than 10. So we got mother net 5. The mother net 5 is a final network, so we need to visualize it. So we use TIFF plot this function to write it out. Here it goes. Now the network has been generated. Okay, this is a network generated using sparse function, and we can compare the two networks generated using two methods. Okay, let's compare them. Here it is. So finally, we have two networks constructed using two different methods. Okay, let's compare these two figures. So this figure constructed using plot network is very beautiful. You can have different information of different phylums and different classes. Also, you can see the connections connecting them. So, but in the network constructed with sparsity, we can see more detailed information, such as bacteria taxa, negative and positive relationships among different taxa, but color of different edges in the network, size of the nodes showing the significance of specific taxa in the network. Also, since we know the p-value for each edge is smaller than 0.01, so we can safely tell that the edges, the correlations among different bacteria classes is very reliable. So in summary, the sparsity-based network is more reliable and informative. So I recommend using sparsity to construct correlation network. So that's all I want to present today, and please let me know if you have any concerns. Thank you all for your time.